In this video, we are going to be focused on linear models and residuals and what is known as LSRL, or a linear squares regression line. So you'll be given several formulas, what does a linear model look like, etc. Okay, so just as we did in the last chapter or the last unit, we talked about normal models. Remember that a model just represents a situation. So we use normal models to represent what the mean and the standard deviation was for a certain amount of, or for the information. Little typo there, sorry about that. A linear model shows, so a linear model is going to show the association between two quantitative variables. So what a model's purpose is to simplify reality to help us understand what the patterns and the relationships are going to be. Okay, so in your head you're thinking, okay, what is a linear model going to look like? So it's going to be a line through the data. So here we have a scatter plot representing, I'm not sure what the data actually, I know that it says temperature in degrees Celsius and the dollar amounts here, but I don't have any more information than that. This line that goes through the data is what our model is. It represents what approximately all of these scatter plots is going to be. The model doesn't contain all the points in the scatter plot. It contains most of them, and it goes through the center of them, but it doesn't contain all of them. Okay, so we have what are called residuals. All right, so let's write on here that, and we're going to talk about this later, that what the points on the line are the predicted values, and these are the actual values. Okay, what we think are the predicted, and the actual is what happened. I'm using those words to hopefully help you focus on the differences between what's not on the line and what is on the line. That basic understanding is really important as you solve through the various problems and multiple choice problems and free response questions and all that stuff, okay? All right, so the residual value, and later we'll talk more about this, is the difference between those. The residual, if you think about what the word residual means, it's the leftovers. Okay, so if we think this is what's going to happen, the difference between what actually happened and what we think happened is that residual value. Okay, so here's the notation, first of all, for the predicted value. So this little hat, and yes, we call it y hat. Okay, so y with this little hat on it is called y hat. So whenever we're talking about the predicted values on this line, we denote that or show it with a y hat value, or y hat is what it represents. The hat means it's the predicted value. Okay, so in the picture before, I just showed you that the residual is the observed value minus the predicted. So the observed, that's what I was calling the actual. Okay, so in the marriage data that we were looking at, the difference between the women being younger or the men being younger and being off the line or above the line or below the line, okay, that's what we're looking at. So we're going to get positive or negative values depending on if the observed is greater than the predicted or if it's less than the predicted or whatever, okay? So this is exactly what you need to have written down in your notes, okay? And maybe you want to write in the words, the observed minus the predicted, so you make sure the direction is correct. Okay, so a negative residual, so remember E, we'll see that later, this is the residual. Is equal to y minus y hat, okay? So when this value is negative, that means that the predicted value is too big. The only way we would get this to be negative is if the y hat is an overestimate, because this is larger, okay? So when it's positive, it's an underestimate because the predicted value is going to be less, okay? So if you want to look at that in the picture, when this is greater, the y hat is greater than the y, it's an overestimate. This is a This is a greater distance, so we get a negative number. If we're looking at the value here, down to the y hat, the actual number is greater, so this is going to be positive. Okay? This example. The residual is negative. Residual is positive. The residual is negative. Okay? Okay. So the least squares regression line. There's a lot of I guess I'm going to say there's math behind how we create it that isn't as important. The reason, well, first of all, when you have the least squares regression line and you add up all the differences between the residual and the actual value, or I'm sorry, when you add up all the residuals, they cancel each other out because that least squares regression line is going to go between where all of these points are. And the better that it is an estimate, right, it's going to go through the middle of all of them. And when we add all these residuals up, they cancel each other out. Okay, so we don't know, we can't look at it if it's a good estimate because the residuals will cancel each other out. So we square those differences because then they'll all be positive. The smaller the sum, the better the fit. You're never actually going to be figuring that out. Okay, so the line of best fit is created from, that's why it's called the least squares regression line. Okay, so the line of best fit is where we get that from. So those are all the same thing. Line of best fit, linear square or least squares regression line, all the same thing. Okay. All right, so this is what you learned in algebra. Y equals mx plus b, where the m is the slope and the b is the y-intercept. Remember, from about 8th or 9th grade, you've been learning what this slope y-intercept form looks like. It is no different here. We still are going to be creating a line. Okay, so in this same exact form, the difference we have here is y hat represents the predicted value, or our y value, because it's on this predicted line with all these scatter plots. Okay, so this line is the least squares regression line. Okay. All right, so b sub 1, it's in the same position as the slope. So you need to remember that the coefficient of the x is always going to be the slope. We're calling it b1 just so that we can use it in the formula that you're going to use to figure it out. b0 is the y-intercept. Okay, so you're not creating a whole different equation. It's the same values. It's backwards from this, but it doesn't matter. The coefficient of x is the slope, and the b0 is the y-intercept. Okay, and I'll talk more about what those mean as well. Okay, so again, y hat, those are our predicted values. You will always write the least squares regression line with y hat. Okay, what it says is that this model that we have, it's going to show what our predictions are. Our predictions follow a line. The better the model is, the data values will scatter closely around it. Okay, so you should have this in your notes if you want to write the y equals mx plus b as a remember, so that you remember it. Okay. Now we're gonna in class probably on Tuesday, I'll show you how you create this regression line in your calculator. But for now, we'll be using some formulas to create it because the way the questions are asked, you need to know both. Okay. So again, the slope is b1 and the y-intercept is b0. So this, you need to write these two down, and I'm going to keep going back in this and talking about the writing in the context. Lots of questions have you write the slope in context of the problem and also the y-intercept in the context of the problem. So remember that slope means the change in y over the change in x. So it tells us how rapidly y hat is changing with respect to x. So if you remember this, that for every unit of y increasing, you'll talk about the change in x. Okay, so that's kind of the formula, if you will, for how you write your answer to explain the slope in the context of the problem. Okay, so please, when you're doing your homework, make sure you're checking that your writing out of the answer matches what's in the book. Okay, the y-intercept, remember that that's where it crosses the y-axis. Okay, so if my linear squares regression line looks like this, it's where it crosses the y-axis. So it's when x is 0, what is y? That's the y-intercept. So again, in the context of the problem, you're going to look at the x variable and you say, okay, well when that's 0, the y hat or the predicted value is blank. Okay. It may seem odd, but it's really just a formula to plug those numbers in, the words, okay? Okay, so here comes what looks like a scary formula. Okay, so here's the slope. I don't know if I've used this word, but when we have two quantitative variables, it's called bivariate data. Okay, so two quantitative variables. Okay, so SY is the standard deviation of the Y values, of one set of values, but it's going to be, maybe I don't want to write Y values, but well, Y in this case doesn't mean Y hat, okay? It's just it's the standard deviation of that set of data, okay? And SX is the standard deviation of the X values. So like if you're putting this in L2 maybe, and you put this data in L1 to figure out what the relationship is, that would be, this is just for example. This isn't always going to be in L2, not always going to be in L1, okay? But what your X values are and what your Y values are when you're putting this in your calculator. And your calculator will come out with the standard deviation of Y and the standard deviation of the X values, okay? We'll actually be putting words in here, so it will help with the context of the problem. Okay, the R is the correlation. Okay, so the correlation times the standard deviation of Y divided by the standard deviation of X. That's how you find your slope. Okay, to find the y-intercept, you use this, and y bar is the mean of the y values. B1 is the slope, and x bar is the mean of the x values. And again, you're either given this or you're calculating it in your using your calculator. Okay, so the intercept is always in units of y. Okay, because it's when x is 0. Okay, so another important piece of information: every least squares regression line goes through the mean x value, comma, the y x value. Okay, I have seen this question asked, so make sure you make a note of that. Okay, all right, let's go through a quick example. All right, so here could be an example of the information that you're given. Okay, so random sample of 30 U.S. farm regions surveyed during the summer of 2003 produced the following statistics. So the average temperature is my x value. The x bar is 81, standard deviation is 3. Average corn yield per acre in bushels is this information here, and the correlation is R equals 0.32. Based on this study, what is the mean predicted corn yield? Okay, well, this is what that's asking for. What is the mean predicted corn yield for a region where the average growing season temperature is 76.5? Okay, so there's my temperature. What's the predicted value going to be? Okay, so that tells me I need a line, and I'm going to plug in my x value and come out with my y hat value. That's what I need. Okay, so we're going to calculate B0. We're going to calculate B1. So have your calculators in front of you so you can do this problem with me. Okay. All right. So the slope. Let me just look back at this. Okay, so the slope is, I get it. Okay, so the slope is B1. So the slope is going to be R SY over SX. So the slope is going to be, the R is 0.32. I love these plug and chug kind of formulas. SY is 5 over 3. So B1, using your calculator, is 0.53. 0.533. Okay. B0 is going to be 131, because remember it's y bar minus x bar, oh, I think I wrote it, times B1. Okay, so B0 is equal to 131 minus 0.533 times 81. So B0 equals 87.8. Okay, so we're going to write in the context of the problem. So the predicted yield is going to be equal to 87.8 plus, and now I'm just putting it in, right? This is my y-intercept. My slope is 0.533 times the temperature. Okay, I'm boxing it so that you see that it's the it's how we're going to figure out the predicted value, not that this is the answer yet, okay? So the predicted yield is going to be equal to 87.8 plus 0.533 times whatever the temperature is, okay? So if the temperature was 0, my y-intercept is 87.8. So if the temperature is 0, my predicted yield of the corn would be 87.8 bushels. Okay, so one way to write that. All right, so now we have to figure out the problem. So the average, the predicted corn yield where the temperature is 76.5. So yield, oops, I'm going to write it down here, sorry. Okay, so yield hat is equal to 87.8 plus 0.533 times the temperature, which is 76.5. Okay, so yield hat, when the temperature is 76.5, comes out to be 128.6 bushels. That is the answer to the question. That's the answer. Okay. The other thing I should have said is the slope. All right, so in context of the problem, the slope means for every 0.533 bushels, average bushels produced, we should see an increase of there's an increase of 1 degree in temperature change, okay? So 0.533 bushels produced. I'm writing this very quickly here in the lower corner. We're going to talk about this. 0.533 bushels produced for every 1 degree increase. Okay. All right. That is the end of this video.